Okay, hello everyone. Let us continue the fourth part of today's class. Okay, in the third part of the class, we have reviewed L. Okay, L is defined as 30 times R max squared over 3 minus 2 times the square root of 2 times lambda bar minima. Okay, what is R max? Okay, let us review. Okay, R max is the maxima reward, which is defined the maxima of summation S, where S is in capital SI. Okay, what is capital SI? Okay, capital SI is the finite state space of the ith channel. And here 1 is less than or equal to I, and I is smaller than or equal to capital K. And then what is lambda bar minima? Okay, lambda bar minima is defined as the 1 minus lambda max. And lambda max is defined the maximum of lambda I, where I is greater than or equal to 1, and I is smaller than or equal to capital K, and lambda I is the second largest eigenvalue of Pi, and Pi is the transition probability matrix of channel I. Okay, let us go back to equation 1.4. So d bar I is defined as 4L over mu star minus mu sigma of I squared. Okay, then what is mu star? Okay, let us review what is mu star. Okay, mu star is defined as mu sigma of 1, okay, which is the greatest mu I. Okay, that is the greatest stationary reward mean. Okay, the intuition is that the smaller the difference between the channel reward means, the more samples we must take to infer which one is better with sufficient accuracy. Okay. Okay, the smaller the difference between the channel reward means, that is mu star, okay, minus mu sigma of I. If this term is smaller, okay, then the d bar I becomes greater. Okay, so that means we need at least d bar I log t times to explore a bad channel sigma of I. So the more samples we must take to infer which one is better with sufficient accuracy. Okay, since the channel reward means are unknown, however, we replace mu sigma of I with this estimate value, which allows us to estimate d bar I. Then we can use the estimate of d bar I, which is updated dynamically during time and controlled by the estimate channel reward means, to design an adaptive sequencing rule for sampling channel I. The designed sequencing rules decide whether to enter an exploration epoch or an exploitation epoch, and are adaptive in the sense that they are updated dynamically and controlled by the current estimated reward means in a closed-loop manner. Interestingly, we found that the size of the exploitation epochs is deterministic, and the size of the exploration epochs is random under ASR. In Gaffney and Cohen 2018 B and A, okay, this is Gaffney and Cohen in year 2018 B, and it is A. The authors showed that ASR achieves a logarithmic scaling of the regret with time as achieved by RCA and DSEE. The scaling with the mean hitting time capital M under ASR, however, is significantly better than the scaling under RCA. Specifically, ASR achieves a scaling order of big O of M times log T as compared to big O of M times log T under RCA. Okay. We also showed that scaling with the number of channels and the delta under ASR is significantly better than scaling under DSEE. Specifically, ASR achieves a scaling order of big O of 1 over the square root of delta plus k minus 2 times log T as compared to big O of 1 over the square root of delta plus k minus 2 over delta times log T under DSEE. Extensive simulation results support the theoretical analysis and demonstrate significant performance gains of ASR over RCA and DSEE. We omit the analysis in this chapter and focus on the description of the algorithm. Okay, next we are going to introduce section 1.2.5.1, Structure of Transmission Epochs. As discussed earlier, the design strategy should use the channels in a consecutive manner for a period of time to learn the restless Markovian reward statistics. The RCA algorithm selects channels based on UCB and uses the channel for a random period of time that depends on hitting times used to catch predefined channel states, while the DSEE algorithm uses channels for a deterministic period of time that grows geometrically with time. The ASR algorithm uses hybrid random deterministic transmission epoch lengths, while determining the exploration rate for each channel according to judiciously designed adaptive sequencing rules, as discussed later. This approach allows ASR to achieve significant performance improvements, both theoretically and numerically. Figure 1.2 illustrates the structure of the time horizon, which consists of exploration and exploitation epochs. Okay, let us see figure 1.2. Okay, this is figure 1.2, an illustration of the exploration and exploitation epochs as implemented by the ASR algorithm. During exploitation epoch, the cognitive user uses the same channel that had the highest sample reward mean at the beginning of the epoch. Okay, we can see that it is the exploitation and it's the explore channel I. And again, this is the exploitation and this is the explore channel I. Okay, an exploration epoch is divided into a random size subblock SB1 and a deterministic geometrically growing size subblock SB2. So explore channel I is divided into many subblock. Okay, this is SB1. Okay, and this is SB2. Okay, SB1 of a channel, say I as in the figure, is random. Okay, here is the SB1. And used to catch the last channel state gamma I, okay, observed in the previous exploration epoch. Okay, here gamma I, here is also gamma I. Okay, the ASR's selection rule decides which epoch to play at each time. The exploration epoch is illustrated for channel I only. Okay, exploration epoch is illustrated for channel I only. In general, an interleaving of exploration epochs for all channels with exploitation epochs. For the channel with the highest sample reward mean is performed. Okay. The adaptive sequencing rules decide whether to enter exploration epoch and which channel to explore. The design of the adaptive sequencing rules is discussed later. We define NOI of T as the number of exploration epochs in which channel I was used at time T. Okay, so you can see that here is a NOI. Okay, here is a NOI. Okay, so it is equal to the NOI of T, but we omit the T here. The exploitation epochs are used to select the channel with the highest sample reward mean whenever exploration is not being performed. We define Ni of T as the number of exploitation epochs at time T. Okay, you can see that here is the exploitation, and use best channel 2 times 4 to the power of Ni times. And this use best channel 2 times 4 to the power of Ni plus 1 times. Okay. The structure of exploration epoch as illustrated in figure 1.2. Okay, let us go back to figure 1.2, this figure. Okay, when entering the NOI's exploration epoch, the cognitive user starts by using channel I for a random period of time until observing gamma I times NOI minus 1. Okay, that is gamma I times NOI minus 1. Okay, that is a random heating time. This random period of time is denoted by subblock 1, SB1. Okay, here the SB1. After completing SB1, the cognitive user uses the channel for a deterministic period of time with length of 4 to the power of NOI. Okay, we can see that 4 to the power of NOI minus 1. Okay, but this is for SB2. This deterministic period of time is denoted by subblock 2, SB2. Okay, so this is SB2. The cognitive user stores the last reward state, gamma I times NOI, observed at the current NOI's exploration epoch, and so on. Okay, so here is the exploration epoch. Okay, so here is the gamma I times NOI minus 1. Okay, here. The set of time instants during SB2 epochs is denoted by VI. Okay, then we are going to introduce the structure of exploitation epoch. The sample reward mean of channel I when entering the ith exploitation epoch is denoted by S bar I. Okay. Then the cognitive user uses the channel with the highest sample reward mean, maximum of S bar I for OI, for a deterministic period of time with length 2 times 4 to the power of Ni minus 1. Okay, here, okay, 2 times 4 to the power of Ni. Okay, here we do not minus 1 here. Okay, and you can see that here is plus 1. Here is not plus 1. So the formal exploitation must has 2 times 4 to the power of Ni minus 1. Okay, note that the cognitive user does not switch between channels inside epochs. The set of time instants in exploitation epochs is denoted by Wi. The cognitive user computes the sample reward mean S bar I for each channel based on observations taken at times Vi and Wi. Okay, let us review Vi and Wi. Okay, Vi is the set of time instants during SB2 epochs, and Wi is the set of time instants in exploitation epochs. Observations that have been obtained at the SB1 period are discarded to ensure the consistency of the estimators. Okay, SB1 is here. Okay, here is the SB1. Okay, and here is the SB1. Okay, so within this period, okay, within the SB1 period, the observations have been obtained are discarded to ensure the consistency of the estimators. Okay, next we are introducing section 1.2.5.2 selection rule under the ASR algorithm. Okay, we next describe the selection rule that the cognitive user applies when deciding whether to explore the channels or whether to exploit the channel with the highest sample reward mean. Let tilde Si of t be the sample reward mean of channel I that the user computes based on observations taken from Vc only at time t. Okay, what is Vc? Okay, we have defined Vi as the set of time instants during SB2 epochs. Okay, then let d hat I of t defined as 4L over the maximum of delta and the maximum of S tilde j of t minus S tilde I of t for Oj square minus epsilon. Okay, where 0 is smaller than delta and its delta is smaller than mu sigma of 1 minus mu sigma of 2 square is a non-lower bound on mu sigma of 1 minus mu sigma of 2 square, and epsilon is greater than 0 is a fixed tuning parameter. We discuss the implementation details later. We also define I is defined as the epsilon square. Okay, epsilon is a fixed tuning parameter and is greater than 0 times lambda bar minima. Okay, what is lambda bar minima? Okay, let us review it. Okay, here is the lambda bar minima, and the lambda bar minima is defined as 1 minus lambda max, and the lambda max is defined the maxima of lambda I, where I is greater than or equal to 1 and I is smaller than or equal to capital K, and lambda I is the second largest eigenvalue of Pi, and Pi is the transition probability matrix of channel I. Okay, and over 192 times R max plus 1 squared. Okay, what is R max? Let us review it. Okay, on page 15, we defined the maximum reward by R max is defined as the maximum of summation small s, where s is in capital SI, and I is greater than or equal to 1, and I is smaller than or equal to K. Okay, and what is capital SI? Capital SI is the finite state space of the ith channel. Okay, so this is the definition of R max. As explained earlier, the user must take at least d bar I log t samples from each bad channel. Okay, d bar I is given in equation 1.4. Okay, this is equation 1.4. We have introduced this earlier in today's course. Okay, to compute the sample means S bar I with sufficient reliability. Okay, what is S bar I? Let us review it. Okay, the sample reward mean of channel I when entering the nth exploitation epoch is denoted by S bar I. Okay, therefore the user replaces the unknown value d bar I with its overestimate d hat I of t. Okay, what is d hat I of t? Okay, it is defined in equation 1.5. Furthermore, since d hat I of t is a random variable, we need to guarantee that the desired property holds with a sufficiently high probability. Okay, it is 25 minutes. Okay, see you next time. Goodbye.